So on to chapter 9, which is further hypothesis tests and confidence intervals. But before I do anything, I just need to do a quick recap of chapter 18 from the A-level single maths. So test results for a module T1 are normally distributed with a mean of 65 and a standard deviation of 10. After the introduction of a dynamic new teacher such as myself, the results for a group of 8 students had a mean of 72. Is there evidence that the results have significantly improved at a 5% level of significance? So, going back to how we set up these hypothesis tests, so we start off with, mu is the population mean test score, and we let x be the distribution of test scores. Then we have H0 is always mu equals the original, so mu equals 65. Here I'm doing a one-tailed test because I'm seeing if the teacher has improved the score, so mu is bigger than 65. And my distribution is x is normally distributed with 65 and 10 squared. Yeah, because the standard deviation is 10 and the mean is 65. So here I've got my sample mean, so x bar 8 is equal to, so is distributed with still the same mean of 65, we're assuming under H0, but now my variance is 10 squared over 8. And I'm looking for the probability x bar 8 bigger than 72. So I'm just doing that in my calculator. So menu 7 and normal CD. My lower is 72. My upper is a really, really big number. My sigma is equal to the square root of 10 squared divided by 8. And my mu is equal to 65. The probability I get there is 0.0239 to 3SF. Then I compare that to my significance level. So 0.0239 is less than 0.05. That means I am rejecting H0. And I need my nice summative statement in the end. So there is sufficient evidence that the teacher has had an effect, which is good news for all involved.
So in the hypothesis test in the last example, we had two assumptions: that the value of the standard deviation of the parent population is known, and the underlying distribution must be normal. Okay, the sample is small enough, and so both these assumptions are required to be true. Yeah, using the central limit theorem in the previous chapter, chapter 8. But if the sample is large, then the CLT, the central limit theorem, says that even if the underlying population is not normal, the distribution of sample means is normal, and the sample variance is a good estimate for the population variance. So, summarizing this, it is possible to use a normal distribution to carry out a hypothesis test for the mean, even if the underlying distribution is not normal and all the population variance is not known. Usually we require the sample size n to be 25 or above, or it will say in the question that you can assume the central limit theorem. So I'm going to do a few more examples.
The first example here. So the time taken for a bus to go from Oundle to Frapston has a mean time of 18 minutes. A new roundabout is introduced, which it is hoped will speed up the journey. A large number of observations are taken, following complaints from students that the journey is now taking longer than 18 minutes. From the 50 observations, the mean was found to be 19.1 minutes, with a sample standard deviation of 5 minutes. Investigate the student's complaint, state a suitable null and alternative hypothesis for the test, and carry out the test at a 5% level of significance, stating your conclusion carefully. So we start off as we normally do. So mu is the population mean journey time, and x is the distribution of bus times, and our h0 is mu equals 18, and our h1, again this is a one-tailed test because the student thinks it's taken longer, so it's going to be mu is bigger than 18. Now, we do not know the population variance or the distribution of the times, but because the sample size is large, we can estimate the distribution of the sample mean. So, as sample is large, because n is bigger than 25, that means I can estimate the sample distribution to be normal. So x bar 50 is normally distributed with 18, and sample standard deviation is 5 squared, so I need to divide that by 50 as well. Okay, so now I'm just working out probability x bar 50 is bigger than 19.1, because that is our test statistic. If I do that in my calculator, so again menu 7, normal CD, my lower value is 19.1, upper value really big. Sigma is the square root of 5 squared divided by 50. I'll put an extra bracket in there. And my mu is equal to 18. And I get 0.0599. So for SF. I compare that to my significance level, so my significance level is 5%. So that's 0.0599 is bigger than 0.05. If it's bigger, I'm accepting H0. Then my summative statement at the end, there is insufficient evidence to suggest that the journey time has increased. Okay, so even though we don't have a distribution, we can use a normal distribution because the sample size is large enough. Okay, I'm going to do one more example. So the lengths of the leaves of a certain species of rare plant have mean 8.6 centimeters. A botanist finds a clump of plants and wants to find out whether they are of the rare species. She collects and measures 50 leaves and finds the mean of their length to be 8.36, and the sample standard deviation is 1.2. Carry out the test at the 5% level. So, starting as always, so mu is the population mean length of leaves, and x is the distribution of the length of leaves. Then our H0 here is mu equals 8.6. H1, we're just seeing whether they are the rare species. We're not saying it's bigger or smaller, so this is a not equal to, this is two-tailed. Okay. Again, as sample is large, and is bigger than 25, I can assume a normal distribution. So that means I've got x bar 50 is normally distributed with 8.6 and 1.2 squared over 50. Then probability x bar 50, my value here 8.36 is less than, so I may as well do a less than 8.36. Work that out in my calculator. So my lower here is a large negative number. My upper is 8.36. My sigma is the square root of 1.2 squared divided by 50. And my mu is 8.6. And I get 0.0786. I compare that to half of my significance level because it's a two-tailed test. So 0.0786 is bigger than 0.025. So I'm accepting H0. And nice summative statement at the end. There is insufficient evidence to suggest that the plants are not of the rare species. Okay, moving on to confidence intervals.
Onto confidence intervals. So when you use a sample to find an estimate for the mean of a population, it will not be exactly the same as the true mean. However, it does give you an idea of the location of the mean. So instead of just giving the estimate, it's often useful to give a confidence interval for the mean. Whenever you see trials or any big stats investigations, there's usually confidence intervals involved. They're usually sort of like bars which are added on to the location of the mean. It's important that you understand what is meant by confidence interval as well. So if you find a 90% confidence interval, that does not say that there is a 90% chance that the mean lies within that confidence interval. What it means is if you take many samples of the same size and construct a 90% confidence interval from each one, then 90% of the intervals will contain the true population mean. Okay, it's quite a subtle difference, but it's a very important difference. Okay, how do we calculate the confidence intervals? So the confidence limits to the mean are based on a sample size m, taken from a normal population with standard deviation, sigma, and given by x bar plus or minus z times by sigma over root n, where the value of z depends on the percentage confidence interval you are using, and these values are in your formula book, or you can do them by doing an inverse normal calculation. So I'm going to show you where they are in your formula book and do some more examples.
So these values of z are in your formula book as shown. So here they are. But you need to be careful as to which one you use, okay? Because confidence intervals are always two-tailed. So hopefully it's all refocused. There we go. So for a 90% test, you're using z equals 1.645. But in the printout, that is in 0.95 value. The reason is because confidence intervals are always two-tailed, so you need to do the 90% instead. Then 95% z is 1.96, and 99% z is 2.576 for the same reasons. Okay, so I'm just going to do a quick example. The results from a particular test are known to be normally distributed with a standard deviation of 10. A group of 8 students take the test and the mean score from the group was 72. Construct a 90% confidence interval for the mean score for the test mu. So, for a 90% confidence interval, I've got z equals 1.645. And we know from our formula the confidence interval is x bar plus or minus z sigma over root n. So my mean is 72, that's my sample mean, plus z, which is 1.645, times my sigma, which is 10, divided by square root of my n, so square root of 8. Okay, put that into my calculator, and I get the confidence interval, which we usually write in interval notation of 66.18 and 77.82. And for part 2, the national mean score for the test is later found to be 65. With reference to a confidence interval, what can you say about the mean score of the group of 8 students? So, confidence interval is completely above .65, so there is significant evidence that the group of 8 students have a mean score higher than the national mean score. So here our confidence interval is 66.18 to 77.82. Okay, but the national is 65. So because our sample, all the values, the confidence interval is bigger than 65, that means we have got sufficient evidence to say that we've got a significant result. Okay.
So for a nice little summary of confidence intervals. So if a confidence interval contains a given value, then there is insufficient evidence that the population mean differs from this value. Okay? Basically, if you get a value in your confidence interval, then there is insufficient evidence that it's different, so we're accepting H0. If a confidence interval is below, then the population mean is less than the given value, and if the confidence interval is completely above, then the population mean is greater than the given value. Okay, that should make sense if you think of it in terms of graphs. If I have two confidence intervals and they overlap, then there is insufficient evidence of a difference between the population means. Even if they just overlap slightly, they just need to overlap. And if two confidence intervals do not overlap, and the confidence interval for, say, mu A is below the confidence interval of mu B, then there is significant evidence of a difference between the population means from which the samples were taken and that mu B is bigger than mu A. That should be reasonably straightforward in terms of thinking of it in terms of graphs, but I just thought I'd surmise it nicely before we get back to some more involved examples.
So let's go back to that bus as an example. So the time taken for a bus to go from Oundle to Frapston is normally distributed with a mean time of 18, new roundabout introduced. Hope will speed up the journey. A large number of observations are taken, following complaints from students that the journey is now taking longer than 18 minutes. From the 50 observations of the journey time, sum of t equals 955 and sum of t squared equals 19460. Find a 95% confidence interval for the new mean journey time. So I need to work out some values. So first I'm going to work out t bar. So t bar is just going to be sum of t over n. So that's 955 divided by 50, or 19.1. Okay. Now I need to work out my sample standard deviation again. So we should remember what our sample standard deviation formula is. If not, it's in the formula. So that's going to be sum of t squared minus n t bar over n minus 1. So that's the square root of 19460 minus 50 times 19.1 over 49, which gives me 4.989 roughly. So for a 95% confidence interval, I've got Z equals 1.96. Then my confidence interval is x bar plus or minus z s over root n. So that's 19.1 plus or minus 1.96 times by 4.989 over root 50, which gives me the confidence interval of, if I do this, so 19.1 plus 1.96 times 4.989 over root 50 gives me 20.48 for my upper value, and for my lower value I've got 17.71. Comment on the student's complaint. So since original mean of 18 is within the confidence interval, there is insufficient evidence to suggest that the journey time has increased. So we get the exact same answer as we did with our previous example, we've just proved it in a different way. Okay, one last example. So finally, a biologist is studying a shoal of fish, which he thinks is either from species A or species B with those mean weights. The weights of both species are normally distributed per standard deviation 80. The biologist catches and weighs a sample of 16 fish. Their total weight is 8864. By 95% confidence limits for the mean weight of the fish. Based on your confidence interval, what should the biologist conclude? And the biologist wants to determine whether the fish are species A, species B, or neither. With 99% confidence, what is the minimum number that she needs to weigh? So to start off with, I've got x bar 16 is going to be equal to 8864 divided by 16, which is 554. And for a 95% confidence interval, I'm going to have to use z equals 1.96, where my confidence limits are x bar plus or minus z sigma over root n. So confidence interval is going to be 554 plus or minus 1.96 times by 80 divided by root 16. That gives me confidence intervals of 514.8 and 593.2. What does this tell me? So the CI contains the mean weight of both species, A and B. So the fish could be either species. So this is an example of those overlapping confidence intervals. Just because there's a slight overlap between them, then we don't have enough evidence to say whether it's A or B with any significance. Okay. The biologist wants to determine whether the fish are species A, B, or neither. With 99% confidence, what's the minimum number that she needs to weigh? So that means the confidence interval needs to be less than 60 grams. So z sigma over root n must be less than 30. Yeah, because there's a 60 gram difference between them, and because I'm doing a plus or minus, that means that must be less than 30. So for 90%, for 99%, my z is equal to 2.576. Therefore, I've got 2.576 times 80 over root n has to be less than 30. Solving that equation gives me n equals 47.3. So needs to weigh 48 fish. Okay, that's it. That is further maths stats done.